Hello. Unit 15, we get into buffers in Unit 15. And for some reason, which I haven't figured out yet, buffers is always really a challenging topic. So we're just going to dive in and see what we can do. All right. So we're going to start with this unit, this section that I skipped in class. Okay, so we're going to just go back to this one real quick and take a look here. There's this thing called the common ion effect. So common ion effect is what happens when you have an equilibrium system and you add one of the ions that's in the system. Okay, so the common ion in this system, you can see there that the equilibrium system in this example is with the weak acid HF. Now, the common ion comes in because if we add sodium fluoride to the solution, it dissolves and gives us Na ions and F minus ions. So F minus is our common ion. All right, so our equilibrium system is the equilibrium between the HF, which is our weak acid, which yields reversibly H plus and F minus. Okay, if we throw in sodium fluoride, that's going to add more F minus. And we know from Le Chatelier's principle that increasing the concentration of a product is going to cause the equilibrium to shift in the opposite direction. So if we add more F minus, in this case, it's going to lower the pH because we're going to shift the equilibrium back towards the undissociated HF, which decreases the H plus concentration. And remember, pH and H plus are inverse. So if we decrease, it's going to increase the pH because it's inverse. So we decrease the H plus concentration, the pH goes up, goes towards closer to neutral. Okay. So what happens here is this common ion effect happens a lot, and we did this in some of the cases in our Le Chatelier's principle lab, where we specifically added or took away an ion, but adding an ion is where the common ion comes in. Okay, so just like I was saying a second ago, according to Le Chatelier's principle, if you add an ion, the equilibrium is going to shift to the other side, because it's going to try to remove that excess ion. So in this case, it's going to shift to the left. There'll be fewer H plus ions, so that's going to impact our pH. Okay. All right, so now we're going to go through the example. Now, when we have a weak acid system like this, first thing we need to do is think about what's in the solution. Okay, remember, weak acid means that one of the primary species in the reaction is the weak acid itself, the HF. Because remember, weak acids do not dissociate very much in solution. Okay, now we have HF, and then we also are mixing in sodium fluoride. All right, so we have, in the 1 molar solution of sodium fluoride, we have dissolved Na plus ions and F minus ions, okay? So that in the solution we have HF, F minus, Na plus, and water. Now in this case, the Na plus is a spectator ion, so it's not going to do anything. So what's really of interest is the HF and the F minus, okay? Now, left to its own devices, HF is going to only dissociate a little bit. But in this case, we're intentionally adding more of that F minus ion. Okay, so the two that really matter in this case are the HF and the F minus. All right, so if we go to our ICE chart, instead of having 0 and 0 for the products, we have 0 for the H plus, but we have a 1 molar solution of F minus because it's a combo. It's a combo of H plus and sodium fluoride. So there's where the common ion comes in. We're not starting at 0. Now the equilibrium is going to still shift to the left. We're going to have minus X plus X plus X because we're starting with 0 of one of the products. We have 0 of the hydrogen ion. Okay, so when we fill in our change. Now we can use our approximation again because the size of X, the dissociation is going to be so small because it's a weak acid system. that we can ignore the X on both the HF and the F minus. Okay, so every equilibrium problem starts with an equilibrium expression. So write that first, and then we plug in what we know. Okay, and we're going to solve for X. Well, in this case, it's really easy because we have the same concentration of HF and F minus. Okay, remember, HF is our acid, F minus is the conjugate base. Okay, so there we go. There's our hydrogen ion concentration. We take the negative log of that number, and we get the pH of our solution. Okay, so the pH is going to be slightly higher than it would be if it was just the acid by itself. Okay, because remember, by adding that F minus, we're pushing the equilibrium to the left, decreasing the H plus concentration. Okay, that brings us to the end of section 15.1.